In the last session or two, I've talked about how we can use the same methods when we drop a stone to calculate the motion of an electron or a charged particle in a uniform electric field between two parallel plates. Now, in the last session, I only talked about what happens when the electron moved in a straight line, or like when I just drop a stone and the stone falls straight down. Now, what I like to do now is to look at what happens if the electron is given a horizontal velocity, or a velocity perpendicular to the electric field. Just like when I throw a ball horizontally, I would expect the ball to move in a curve as it falls and hit the ground. So I want to calculate the motion of the electron. If it is given, say, a horizontal velocity in this example, we would expect it to curve under the force, under the electric force. So let's see how we would calculate this. Now, in the case of a ball that I hold in my hand, for example, suppose that I give it a horizontal force. Suppose that I give this ball not the horizontal force, but the horizontal velocity. I'm going to throw it forward at a certain speed. Let's say the speed u. Okay, let me call this ux. I'll call this ux. So the ball would fly outward, and it will fall along a curve, and then it will hit the ground. And suppose that I want to calculate at what angle the ball hits the ground. When the ball hits the ground, it would be moving at a certain angle. Okay, I want to find what this angle is. So let's say this angle is theta. I want to find what this angle is. But the way to do this would be to resolve the motion into two directions, the horizontal and the vertical. The horizontal motion has no force involved because the gravity acts downwards. So for the horizontal motion, the horizontal velocity, the horizontal component of the velocity must not change. Right? It must stay constant. So if I look at, for example, this velocity just before it hits the ground, I can think of resolving it into two components, a horizontal component and a vertical component. Now I would expect the horizontal component to be the same as the starting velocity, ux, since there's no horizontal force to change it. We are neglecting air resistance. Okay, because the weight only acts downwards. It would only change the vertical components of the velocity. So let's say, so the vertical, the horizontal component ux would remain the same, and we want to find the vertical components. Let me call that u y. Now this resultant direction, this final direction of the velocity, it would be the diagonal of a rectangle with these two components as the sides. Okay, so if we know both ux and uy, we would be able to find the angle theta, because tangent theta will be related to uy and ux. So assuming that we know the starting velocity, I want to find what the final direction is. This means that we need a way to calculate the vertical velocity uy. But we already know how to do this. That was exactly what we did in the last two sessions. Okay, so let's say the height of the ball when I first throw it, I'll call it d again. That's the height of the ball. For the vertical motion, the vertical component is 0 in the beginning because I threw the ball horizontally, so there's no vertical component. So the vertical component starts from 0, and I want to find out what the vertical velocity is after the ball has fallen over the height d. Now, if we recall the formula that I used just now in maybe 2 sessions ago, or even in the last session, the formula was uy squared, that's the final velocity squared, is equal to the initial vertical velocity. It might be easier if I write out the full formula. The acceleration equation that I want to use is v squared equals to u squared plus 2as. So that's the standard equation, one of them. And for the vertical motion, just the vertical part of the motion, v, the final velocity, will be uy. So v is uy. U, the initial vertical velocity, is 0 because initially velocity is all horizontal. So that's u0 squared for this, plus 2a is the acceleration due to gravity, which is g, as the vertical distance moved. Remember that we are applying this equation now to just the vertical components. So the vertical displacement is d. So from this we can find uy by taking the square root. Once we have uy, and assuming that we know what ux is, we can then find the angle theta, because tangent of theta must be equal to uy over ux. Okay, from this right angled triangle, we know that that's the right angle here. So that's the way. This is the way that I can use to find this angle. Now let me now look at the problem for an electron going through these two parallel plates. Suppose now that I have an electron starting from here, starting from one end of the plate. Now I previously explained that the electric field is really only uniform when you are further away from the two ends of the parallel plates, because at the edge the field lines will be curved, and the electric field strength will start getting weaker as I start moving as I start moving to the edge and goes out. So suppose that, but for now, let me just assume that, just to make things simple, that the electric field strength is uniform all the way until the edge. Okay, let's just make this simple assumption. And suppose that this has a certain initial velocity at the point where the electron enters the field. So that's my electron. It enters the field at a certain velocity. I'll call that ux as well. And because of the electric force in between the plates, okay, the negative charges there would repel the electron. That would be a downward force. So that would be a downward force. And this downward force would cause the path of the electron to bend, just like the path of the stone bends after I've thrown it. So the electron path will bend under the field, it will curve until it reaches the other end of the two plates, and then it will travel straight out with a certain direction. Now if you compare this description with throwing a ball horizontally, you can see that they are very similar. If we would have a different mass for the electron, we would have a different force on the electron. But apart from that, the physical idea is very similar. If electron flying horizontally, force vertical, so we can expect that using the same equations, the same acceleration equations and the same steps, we should be able to find, for example, in this case, I might be interested in the angle. All right, the angle, the bend angle as the path goes through the field. Say this angle theta to the horizontal. I should be able to use the same method to find this angle. So let's try that. Let me write in more of these components. So I would expect that the horizontal component ux remains the same here because the force is perpendicular to it, and that the vertical component uy, there would be an increase in the vertical velocity because of the force. Now let me try and calculate this angle. I'm going to use the same values for the parallel plate that I've used in the past 2 or 3 videos. Let me start with the velocity ux. I'm going to take a big value. I'm going to use a big value for this. Let me say 726 followed by 4 zeros meter per second. Okay, so I just made up this number. It is actually 10 times bigger than the speed that I calculated in the last video for when the electron moves vertically from the top to the bottom plate. But now, for now, I just take this as an example, speed of the electron. So starting with this speed, right? And I need to know, or some way to find the vertical acceleration as well. And this would depend on the electric field. So I would be using the same voltage, and plates would be at the same distance as before, 1 centimeter. So I would expect the same force and same acceleration as before. Right, so without going through the details, repeating the details, I shall just write down the acceleration that I got from the previous video that I obtained by calculating the force from the voltage and distance. So this is from the last 2 videos. Okay, from the last 2 videos I had the acceleration as 2.68 times 10 to the power of 13 meters per second squared. Okay, so for now, just we will take this as given or obtained from the last session or 2. So in order to calculate this angle, now we know from the method I described for throwing a ball horizontally, I must know ux and uy. Ux we already know. Ux, the horizontal component, is the same as the starting value. Okay, so that's known. Uy, in order to find uy, we need to go through these acceleration equations, and we find that we need to know the acceleration, okay, which we do now, and we need to know the distance. Now in this case, actually, I don't know the distance. Okay, I don't know the distance. So I can't use this method. But I can think of another method I can use, also using maybe a different acceleration equation. Now this other method is this. Instead, I can first find the time it takes to travel from the left side to the right side. Now if I can find the time, then I can find the change in the vertical velocity from the vertical acceleration. Okay, recall that there is a formula. V is equal to U plus AT. This is the first acceleration equation, where we can find the velocity from the initial velocity and the time. Okay, so if I can find the time it takes, since we already know the acceleration, if you can find the time it takes between the starting and the final position, I can use this to find uy. So let me just clarify what we are after. So the acceleration there is a, is this one. The v there is the uy. So I'm thinking to apply this acceleration to the vertical component, right? Just the vertical component. The horizontal component does not accelerate. And u is the initial vertical velocity, which is 0 because initially the velocity is purely horizontal. So this is 0. Okay, so all that remains now is to find t. If I know t, I can find uy. How do I find t? T from between here and here, t is we would be able to find t by using the fact that the horizontal velocity, horizontal component does not change. And we can find it if we know the length of this plate. Right, so that's one more information that I need to know. So let me say that the length of this plate is 10 centimeters. 10 centimeters from there to there. Okay, I'll represent this length by L. I'll call this L. So, okay. So therefore, we know how velocity and length and time are related. So the time, therefore, the time should be equal to the distance L divided by the horizontal velocity ux. So L over ux. Now we know L is 10 centimeter, which is 0.1 of a meter, and we know ux is given here, right? This big number here. So we can substitute these two numbers into here and find the value for t with my calculator. Okay, and the answer that I got is a very small number. It's 13.8 nanosecond. Right? Remember, nano is 10 to the power minus 1. So with this, I can now use this equation to find uy. So uy, therefore, is equal to, this is 0, a times t is equal to a times t. Now a is equal to this acceleration, the vertical acceleration, and t is this time given here. Must not forget the 10 to the minus 9. So substituting this number and this number into here and here, I can then use my calculator once more to find 363,000 meters per second. So that's uy. So I now have the answer for uy, the vertical component, at this point. And I know the horizontal component ux is the same as the starting velocity. So finally, I can find the angle theta using this same expression here. So let me write this out. And the angle theta is therefore the inverse tangent of uy over ux. Inverse tangent of uy over ux. And now I know that ux is this value, this number, uy is this number. We're putting those two numbers into here and here. The answer I got is 2.86 degrees. So this gives me the bend angle of the path of the electron, right, after it travels through the length of the parallel plates.